Let us try now to explain to you the reason why I carry out all these modifications. I'm going to start with this centre coupling. This is the original that's just been taken out of the engine. The first thing you'll notice is that around here it's covered in black mastic. Black mastic's alright if you're sealing up double glazing windows. Putting it inside your engine, I don't believe, is very clever. You saw how easy it was for me to pull those bits off. If they come off and end up going around your engine, you can work out the results. So I make a new hub to replace this one. In the back it has a machined recess which accepts an O-ring. So now we have no need of the black mastic. The silicon sealer, I think it is called silicon gasket. The other problem with the silicon gasket is that it also coats this face. I can scrape some off. There is evidence of it on this mating face. Now that mating face is very important. The reason it is important is twofold, one of which is when that is pulled down tight against the flywheel inside the engine there, if it is in any way fouled, damaged, not exactly square to the axis of the crankshaft, then it will pull this entire thing off centre when you tighten the nut. You may not think that's very much, but if that's a few thousandths of an inch off centre, it doesn't do any good to the balance of this thing, and it's part of the reason why I believe in the past people have suffered broken crankshafts. It has to be said that most of those were with the previous cush drive, which was solid steel, much heavier than this one and equally likely to be out of balance. The other thing that happens with this little assembly here is that if we've got a nice clean face mating up against the crank web, the shoulder on the crankshaft if you wish, then tightening the nut onto it very tight creates a thing called a compound bar. We have the crankshaft going through the middle, which is in tension, and this sleeve over the outside, which then comes into compression. Effectively, we have changed the 1 1/8 inch diameter crankshaft into a shaft which is now 2 inches in diameter. Much more rigid, probably by a factor of 10. I haven't done the calculations, but I'm fairly sure you'll find that's where it is. The importance of that stems from the way this thing drives. This is an original rotor with the roller as supplied. Now you can see that if that is going to push the inner rotor round by being moved up to one side, well, it is pushing across the diameter of the coupling, a sideways force. It uses a wedging action to drive. Now if there are two of them, one here and one here, opposite, then they balance each other out. Maybe not perfectly, but well enough. We all know that these things deteriorate. If you get 10,000 miles out of a set, you've been very lucky. When they deteriorate, I can tell you because I've taken lots of them apart, they don't all deteriorate at the same time. Inevitably one of them turns to dust first, and then another one, and then finally the thing gets all out of control and turns into a blender and you've got nothing left but dust. But during that period, when one of these has disintegrated, its opposite number is pushing with no resistance. It is pushing this thing sideways. It is therefore extremely important that this assembly here, the crankshaft and its sleeve, are as stiff and resistant to bending as possible. Otherwise you risk snapping it off. And you can work out for yourself what sort of bill that brings with it. Quite apart from strength, this little piece here carries out another function. It has an oil seal which runs on it. This is a nice new one, and on the inside, you probably can't see it from there, but take my word for it, it has a sharp knife edge of rubber material. It's flexible, has a little spring in the back to hold it tight against the shaft. Rubs on here. You can possibly see the little shiny line where it runs. Now this one has a turned finish. You can possibly even hear my fingers running over a surface which is somewhat finer, but nonetheless not dissimilar to an old gramophone record. That is not satisfactory for running one of these seals. Those are not my words, they're the words of SKF who make the seal. The other problem is that for some reason which is entirely beyond my understanding, a shaft which in the corner here is 2 inches in diameter for the location of the alternator rotor, which you've just seen me remove, is reduced immediately after where the rotor fits down to 50mm. Now I can tell you that SKF's tolerance for the running of this seal on a shaft, their tolerance for the shaft size is less than 0.5 of a millimetre under size, maximum. This being 50mm is 0.8 of a millimetre under size. It is no wonder that a lot of people suffer leaks because A, their seal has been worn out by the rough surface, and B, because the shaft it's on is 0.8 of a millimetre too small. The one I will replace it with has a high grade finish up to the specification that SKF asked for. It has a nice taper there so that that seal goes on without causing it any damage, and it's 2 inch. This is an American made seal. Little point of interest here, all of these seals are American made. They're made by a company called Chicago Rawhide, who own the patent on steel encased seals. But nonetheless, this was made for the S&S engine. It is imperial in size, 2 inch. You will get a 2 inch shaft. Let's put that to one side and talk about what I'm going to do to it. I machine away that entire top section, this bit. I bore the middle out. It is a steel insert in an aluminium rotor. You can see the darker steel portion inside. That steel rotor, this one, or shall I call it a steel hub, this thing, is made of free machining mild steel. Free machining steel is selected for speed of manufacture, for longevity of the tools on the machine that do the manufacturing. It has got nothing to do with strength, hardness, toughness, or anything else which is required for something that fits into your engine. The splines can be fitted in 3 different ways. When I say fitted, I mean mated together. Good fit, no gaps, no daylight. They can be fitted on the minor diameter, the major diameter, which is at the tops of where these splines are, and on what we call the flanks, so the sides of the splines where they push. I can tell you that the one that comes with your original coupling only fits on the flanks. It does not fit on the major diameter or on the minor diameter. If this thing on the shaft develops any slackness at all, and it will because it's made of soft steel, then there is nothing to stop it wobbling up and down, side to side, because where the flanks mate, the ones on either side stop it from tipping that way. The ones top and bottom stop it tipping that way. Get a tiny little bit of slack in it, and I can tell you most of them just fit easily. Tiny bit of slack in there, the thing starts to rattle, the major and minor diameters are not in contact, and before a few hundred miles are up, you're in for a big bill, and if you don't stop it quickly, it'll cost you a crankshaft as well as a new one of these. The splines in this hub that I'm going to fit are cut by people who cut rotors, or shall I say the blades for rotors on gas turbines. These guys know what they're doing. They wire erode the splines. I have them wire eroded so they are a very tight fit. You will not get one of these to go on that crankshaft without some hand work. You will see me later on hand fitting this to the splines on the crankshaft. I make sure that it is tight, it is fitted to the major diameter, to the minor diameter, and on the flanks. We don't mess about, because messing about costs the customer a lot of money in the long run. Having machined the old part of this hub out, it is machined under size. That won't go in there. The flange fits, I put it in upside down, you can see the flange fits in there nicely. So what we have to do is to make this an integral part of that rotor. We get the rotor hot. You will possibly have seen people on YouTube or somewhere fitting a cartwheel onto an old wooden wheel, a steel rim on an old wooden cartwheel. They get it hot, glowing red hot in their case. That expands it, it drops over the cartwheel, they then throw water on it, it shrinks, and it pulls the whole wheel together and keeps it strong. We're going to use the same principle. I'm going to make this hot, very hot, not glowing red by any means, but nonetheless very hot. This I'm going to keep cold. I measure this and measure this. I continue to measure this while I'm heating it. When I get it to be 0.2 of a millimetre bigger than this, pop, that drops in. As it cools, it clamps on here, and I can tell you now that a shrink fit of that nature is 3 times as resistant to twisting as if we were to put that under a hydraulic press and just press it in. Having got it in, there are 6 bolts that hold it in place. We obviously line those bolt holes up. In between there are 3 smaller holes, and in those 3 smaller holes we drill and ream a tapered hole, and we fit 3 driven in steel taper pins. They are then flushed off with this face. We then bolt the alternator back on. I do not use the stupid countersunk screws that come out of it with a little tiny socket in the middle. I use a conventional cap head screw. I turn the countersink angle on the back of that cap head screw. There is just enough room, and I measure each one to make sure they fit so that they clear the tops of the windings in the alternator stator, and that holds this whole thing together better than when it was new. Another little break for explanation for you. You've already heard me mention these things a couple of times. They are used to secure the alternator rotor, and they're also used to secure the bearing carrier plate in the back of the bell housing, one that carries the clutch. They are soft steel. They are countersunk, which only leaves enough room for a tiny socket in the top there, and if you're not very careful, when you take them out, you end up rounding out that hexagon. For the plate in the back of the bell housing, I use a countersunk washer to fill up the countersink. a high tensile grub screw, an M8 nylock nut. This means that you can put an Allen key in the end of the grub screw, take the nut off, and it means you can get that plate out without having to dismantle the clutch and remove the flywheel. Not that you should ever need to do it, but it might be handy one day. For fixing the alternator in place, I replace those countersunk screws with a standard socket cap head screw, takes a big Allen key, and I turn a chamfer on the back, a 90-degree countersink on the back. Much easier to get undone next time, and considerably stronger in its fastening ability. So we've seen the importance of making this thing a very rigid assembly when it's put onto the crankshaft. We discussed earlier the fact that these rollers produce a sideways wedging action. Well, all forces have an equal and opposite reaction. All actions have an equal and opposite reaction. So it's not only pushing this thing sideways on the crankshaft, but it is also pushing the centre rotor sideways on the shaft, which I'm going to call a counter shaft. This counter shaft which transmits the drive back to the clutch. Forgive me for showing you how this goes together. It goes together like that. The rubbers sit in here and in here, and the rolling back and forth gives you the shock absorbing quality of the drive. As that thing rolls back and forth, it progressively takes up the drive and irons out all those huge torque spikes that everybody talks about. I think this thing is made, let it be said, by Centre, who are world leaders in marine couplings. These people know what they're doing. This is well made, it does its job beautifully. Where I think they've made a slight mistake is in having this curve in here a little bit too flat in the middle. It allows this roller to run backwards and forwards freely and allow 20 or so degrees of lost motion, not lost motion, but free motion in the middle of the travel of this thing before it starts to compress and take up the drive. That is why, if you were to put your Morgan unmodified, put it in gear and just lift your foot slowly off the accelerator, anything less than 2000 RPM, you get this awful dunk business. Makes you look like a learner driver who hasn't learned to use the clutch properly yet. I feel that that is detrimental, A, because it means you've got to do racing starts all the time, and that's no fun if, like me, you have to drive in traffic every time you go out before you can get out of the city. And B, it sends its own generated shock waves back to the clutch, which is why the clutch we looked at earlier, let me go and get it, has somewhere a broken spring. You can see it there, big chunk missing out of it. I suspect that this lashing backwards and forwards contributes to that sort of damage. Makes it uncomfortable to drive, it's not nice. That's why I first started on this project, and the first thing I did was made some rubbers which completely fill the gaps. They don't roll about at all, there is no free motion. The first thing I had to do, I found that it wasn't absorbing enough of the shock, so I put these little beaks in the end which squeeze up. Still, it wasn't absorbing enough shock. I reduced the hardness of the material and put beaks in both ends. Problem I found then, although it was a brilliant machine to drive, take-up was just smooth like silk. On tick-over, these things would make the coupling bounce. That bouncing sets up a thing called gear hammer. Gear hammer is something that Mazda MX-5 drivers complain of. It's a noise which you lose when you dip the clutch, because that bouncing is then no longer transmitted to the gearbox. Lift the clutch, brrr, gear hammer. Very embarrassing when you're sitting at traffic lights. Morgan three-wheeler is the centre of attention anyway, all the more so when it's making all that racket. People tend to point and say, what's that? Like that. Awful. I moved a stage further, giving a little bit of rolling motion in the middle and two big flats to prevent any excess rolling. That worked fairly well. Still I got gear hammer. I've changed the shape of this, and I'm not going to show you the shape of the ones that I put in. It is slightly different from this, just enough to lose the gear hammer. The reason I'm not going to show it to you is that the people who made this tried to rip me off and sell my design as their own direct to the public. I will not give them the chance to do that again. So you will now end up with a car which will, on tick over, with the clutch lifted gently, just purr away down the road. You can, at 1200, 1500 RPM, trickle along in traffic without having to keep stopping and starting. Makes your car a joy to ride. Okay, that's what we're going to do as far as the rubbers are concerned. We are then going to address the fact that these rubbers only last 10,000 or so miles. I don't actually know how long my latest development ones last, because nobody's ever worn a set out yet, but one day they will. When this thing's assembled, there is no possibility that you can, through here, remove those rubbers, because the flange at the back of this centre unit, this central rotor, is integral. It is cast in part of the rotor. There is a removable one at the other end. When you look at it, it's no use having the removable one at that end. You can't get to it. It took me a while puzzling over the fact that this is a marine shaft coupling made by people who have years and years and years of expertise. Why would they build something that if you were at sea and you lost the drive, your only alternative to getting the drive back is to start putting up flares, because if the weather's bad you're going to die? I could not understand why they would build something like that, and suddenly I tweaked the fact that this thing is upside down. If this was in a ship like that, you couldn't get the rubbers out. If the removable flange was at this end, then you could. Okay. There is one of these rotors. It was initially this way up, with that flange bolted on here, and an integral cast-on flange at the bottom. You can't just flip the thing over, because there's a big recess in one end and it would end up in the wrong place on the shaft. So what I have to do is to machine away that integral flange and fit a removable one at the back. Now, when it goes together, you can see that you have access to take those 4 screws out, pull the flange back, and you can change a set of rubbers. The way in which you get access to it in order to achieve that change of the rubbers is via a hole which I'm going to machine in the bell housing here. It's in between the narrowest of the gaps between the webs on the casting, so it doesn't take away very much strength, and it just gives you enough room to get in through there to release these 4 screws, pull the flange back, and then in here you have my latest design of insert, which has a little thing sticking up on the end there with a hole in it. tab, that's a good word, isn't it? A little tab. And you can then pop a screwdriver or something in the hole, pull these out through the bottom, put another set in, or just examine them and put them back again. The job only takes half an hour. It's a lot less time than you'll spend at the side of the road waiting for the AA when they fail. You may ask why this now only has one flange on it. There's a good reason for that. This thing, as we've said earlier, is subject to the same stresses and strains as this one, being pushed about sideways by those rubbers when they fail. And there is only one bearing, it's in there. It's a pretty substantial damn bearing, I have to tell you. It's a double row angular contact ball race. It's a fine piece of stuff, but it was initially installed to take a Harley Davidson style cush drive to face cams, and all of the pressure developed by that is axial. It's along the length of the coupling. So none of this business, none of that going on in the middle, no sideways forces. Same bearing has been retained for this design, and I don't think that that bearing is sufficiently strong, nor would any bearing be, to support a shaft with no support at the other end. So I racked my brains and said, well, how do you make this thing more rigid? And by the way, I have seen these aluminium castings destroyed where the bearing has become damaged and has rattled loose in the casting. I've had to spend quite a lot of time and money boring them out and putting sleeves in to fit a new bearing. You don't want that happening unless you, well, you don't want it happening. End of. The way I make the thing more rigid is, having now turned this thing up the other way, I fit into it an extension shaft. It won't go all the way in until I put it under the press and press it in, but it sits there like that. Inside here I fit a bronze bearing in an aluminium carrier. That gets pulled in there, and it uses the other end of the tapped holes that run right the way through where the alternator bolts on. There's enough room in those holes to get 6 bolts in to hold that bearing carrier in place with its bronze bush. The bronze bush sits on there. It's all wobbling about because it's not assembled. As you can see, this thing is then supported at both ends, down there and now up here as well. People ask me why I use a bronze bush in there and not a ball race. You have to bear in mind that these two items, although they are both spinning at engine speed, do not revolve in relation to each other, except for that little bit of movement in the rubber inserts. So they rock backwards and forwards. Rocking backwards and forwards with a conventional roller or ball bearing will cause something called false Brinelling. Best way I can describe false Brinelling is if you watch someone rolling out pastry with a pastry roller, rolling pin, that produces a nice big flat smooth surface if they are rolling it over a long distance backwards and forwards. If they stop in the middle and just rock it backwards and forwards slowly while still pushing on it, it will cut the pastry in half. That's exactly what happens when you run a roller bearing or a needle roller or a ball race, whatever, and the rollers are just rocking backwards and forwards. So we use a plain bearing. It only comes into its own as a bearing per se when the rollers fail and the units spin independently of each other. And take it from me, that will only happen for a few seconds before you turn the engine off and call the AA. So, we've now got an inner rotor which has been modified so you can take the flange off from underneath. We've got a bell housing which has been opened up so that you can get in there to do the job. We've got inserts with little tabs on so you can pull them out to change them. That entire job can be done, in my case, I've done it a few times, I'm experienced, in less than half an hour. In your case, when you do it first time, it could possibly take you an hour. That will save you probably 10 hours work from a mechanic in a workshop somewhere, pulling the engine out every time when you have to replace these things, which are at the end of the day a consumable. They don't last any longer than a pair of tyres. But a pair of tyres is cheap to change. These guys are not. Thank you very much for listening to all that. I hope I haven't bored you to tears. Now I'm going to move on to the next video and show you how we put all this stuff together. Just to interject for a second, something I missed on the original video. The material this hub is made from is high tensile alloy steel, which has been hardened and tempered to a hardness which is just barely turnable in the lathe. You will not have any problems with this.